Today we're going to be talking about the definition of the derivative. The derivative of f at x is given by f of x, the limit as h goes to 0, is f times x plus h minus f of x over h, provided that the limit exists. Let's go over an example. Find the derivative of f of x equals 2x squared plus 5. Alright, so first remember to carry your limits. We have our equation right there. We're going to go ahead and plug in 2x plus h squared plus 5 for f of h plus x minus 2x squared plus 5. Don't forget to put that part in parentheses for your f of x, all over h. Again, carrying your limit with you. We're going to go ahead and distribute in those terms. We can do a little bit of cancellation here to simplify, and that leaves us with 4xh plus h squared over h. To simplify this further, we can go ahead and pull out an h, which cancels out, and that gives us, pulling down our limit still, 4x plus h. We can go ahead and substitute in the 0 for h here, because we're not going to be doing anything illegal, like dividing by 0. That's going to give us 4x plus 0, which gives us our answer 4x. So 4x is our derivative. So this is the long way of doing it. There are a couple of other ways to do so using derivative rules. So the first rule is the constant rule. The derivative of a constant function is 0. That is, if c is a real number, then d in respect to dx, c equals 0. So an example of this is f of x equals 10. Any constant is going to be 0. The next one is the power rule. If n is a rational number, then the function of f of x equals h to the x is differentiable, and d in respect to dx, x to the n equals nx to the n minus 1. For f to be differentiable at x equals 0, n must be a number such that x to the n minus 1 is defined on an interval containing 0. Here's an example. F of x equals x to the 18. What you're going to do is pull the 18 down into the front, and you're going to minus the exponent by 1, which gives us 18x to the 17. Next one is the constant multiple rule. If f is a differentiable function and c is a real number, then cf is also differentiable, and d in respect to dx of cf to the times x equals cf x. Example, f of x equals 2x cubed. So the derivative, you're going to bring down the exponent like you would and minus the exponent by 1, and you're just going to multiply by the term that is already there, which is going to give you, the derivative is 6x squared. The next rule is the sum and difference rule. The sum, or difference, of two differentiable functions f and g is itself differentiable. Moreover, the derivative of f plus g, or f minus g, is the sum, or difference, of the derivatives of f and g. So here's what the sum rule looks like. It's just d in respect to dx, f of x plus g of x equals derivatives of fx plus gx. And same thing with difference, except for you're going to minus the fx and the gx. So here's an example. F of x equals 4x squared minus 2x plus 6. So I did a little bit of work here on the second term. You're going to see you bring down the 2 to be multiplied by the 4, and then you minus the exponent 2 by 1. In the second term, 2x minus, it's going to be 1 minus 0 for the exponent, and then as we know, 6 is a constant, so it is just going to be 0. Simplify that, and you get the derivative is 8x minus 2. The last rule is derivative of the natural exponent function. D in respect to dx, the exponent to x, is what it is. So an example of this is f of x equals 10 to the ex. The derivative of that is going to be the exact same thing, 10 to the ex. Let's go ahead and look at some example questions. The first one here is y equals 1001. Answer here, because it's just a constant, is going to be 0. Second problem is f of x equals 2x to the 20. What we're going to do is bring down that 20, and then you're going to minus the exponent by 1. And go ahead and simplify. You're going to get 40x to the 19. Next example is f of x equals 5x to the 4th minus 2x minus 8. All you're going to do is bring down that exponent, then you're going to minus the exponent by 1. Then for the second term there, just 2x, and that x has an exponent, an invisible exponent of 1, so 1 minus 0. And then we know that that 8 there at the end, the negative 8 rather, is just a constant, so it's going to be 0. Simplified out, that's going to give us the derivative is 20x to the 3rd minus 2. Next example is f of x equals x to the 1/3. So this is a little bit trickier since it has a fraction as the exponent, but it's the exact same process that we did before. You're going to bring down that 1/3 to the front, then you're going to minus the 1/3 by 1. An easier way to look at this is 1/3 minus 3 over 3, since 3 over 3 is still 1. It's just easier for you to see it. So that's going to give us that the derivative is 1/3 x minus 2/3. A little bit different way to put this is you could bring down that negative exponent into the denominator. So that would give us the derivative is 1 over 3x to the 2/3. Last example is f of x equals 14e to the x, and it's going to be exactly what the problem is. The derivative is 14e to the x.